Welcome to Modern Retrogramming. This is episode 4, Data and Data Types. All programs have to deal with data at some point. Many computer languages either enforce strict rules to make sure data isn't used inappropriately, or they allow different types of data to be mixed and leave it to the programmer to ensure proper usage. Plasma is much like assembly language. Data can represent any type you like: characters, integers, pointers, arrays. It's up to you. Let's create a new file. Look at how data is represented in Plasma. Plasma always calculates in 16-bit words. In memory, however, data can be stored in 8-bit bytes or 16-bit words. Bytes are unsigned, words are signed. Here, a key can only contain the values of 0 to 55. As the Apple II is an 8-bit machine, this is a natural size for much data. Characters can also be represented in 8-bit bytes. Byte and char are synonyms. There is no difference to the compiler of one over the other. Now this defines a 16-bit variable which can be used in a number of different ways. It can also be written with the var. This might convey a better usage of the variable pos. Word var can represent signed values, negative 32,768 to 32,767. With certain usage, it can also represent the unsigned values of 0 to 65,535. Byte and word were the original variable names, but I tend to prefer the char and var usage now. Now, global data is allocated as part of the module, along with its code. Global data can be initialized. Local data is allocated as part of the function invocation and is deallocated when the function returns. It cannot be initialized like global data. Rather, it must be explicitly set with code. Remember, a variable name is just a label for an address. So here we've defined char 3 different ways. And we're going to print them out and show that they're all equal. Now the first two were defined as constants, and the third was defined as a variable. However, when we print them out, they all print out the same value. Now arrays are consecutive values in memory with only one label. The individual values can be referenced with an index. So here we are creating an array named keys of 4 elements. Brackets used in a variable declaration describe the size of the array. We can initialize this array with the characters A, B, C, and D like this. Accessing the array is simple. We use the label name, the variable name, with a bracket index. And here we are actually going to reference them in reverse order. Now note that indices are 0-based. That is, 0 is the first element in the array. So when we print these out, it'll print out A, B, C, D in reverse order. Now Plasma does no bounds checking on array indices. One can fetch keys 100 and get a value. Now this can be considered a bug or a useful feature. It's up to you, the programmer, to ensure this is what you want. As the saying goes, with great power comes great responsibility. So you aren't required to provide a variable label when initializing global data. Here we've created 4 more characters after our array, but we can easily access the letter F with the index 5 off of our variable keys. The variable size in brackets when creating the array variable just specifies the minimum size to reserve for the array. So for instance, we create a name Bobby with an array size of 4. This would reserve 4 bytes for the array, but it would initialize all 5 characters. Conversely, if we only had 3 characters to initialize, it would still reserve 4 total bytes. It isn't even a requirement to provide a size for the array. Here we can just provide an empty brackets and that will then allow us to reference whatever initialized data that comes afterwards. If we provide no initialized data after the label using empty brackets, it actually reserves no bytes, but it can be handy for creating a variable label, then providing the anonymous initialized data in the following lines of code. This is equivalent to the previous example of Susie. We don't even need brackets with initialized data. Again, this is equivalent for referencing keys as an array, even though we didn't explicitly list it as an array when we defined it. Now, there's a special kind of array called a string. Strings are just like an array of characters with the exception of a hidden length byte at the beginning. Plasma has support for creating strings by wrapping the characters in double quotation marks. These are the strings that other languages like Pascal and ProDOS use, where the length of the character array precedes the actual characters. We also can use string literals in our code, just we've seen before in our Hello World program. Here we're just going to replace that with printing out Bobby. But when referencing strings in memory, they can be written easily with the double quotation marks, and it will come out looking as our name for here is, with a 5 preceding the actual characters for the length of the string. So let's test that. Let's actually print the first element of the array and verify that's exactly what we get. So name 3 is our string we've defined using the normal double quotation marks. Name 4 is our hand-coded string that we've placed in memory. Let's ensure that they're the same. Yep, they both have the length of 5. Let's actually go ahead and print the string to the screen. However, when we're printing the variable strings, we don't pass in the variable name. We actually have to pass in an address. Remember, the variable names are just labels of addresses. So since we want to print out the whole array, we have to pass into put string the address to that array, and that @ sign is what tells the Plasma compiler to use the address. And there we see it. We print out 5, which is the length byte, and then the full string. All right, let's clean this up a little bit. Now, words and vars are just like bytes and chars when it comes to initializing, except their elements are 2 bytes in size. So let's create a var array and ensure that we get what we expect. We'll print the 4th element in the array, which is indexed with 3, remember 0 based. And let's see if we print the right variable. And there we go. It prints 1,000. Now the last type is actually just another synonym for byte or char, and it's res for reserve. If you're just reserving bytes, and this can be a more descriptive word than byte or char. We'll revisit this a little bit more when we get to the episode on data structures. But you will note, perhaps, that I'm using the 1.01 version of the compiler. This little data definition brought out a bug in the 1.0 version of the compiler, so make sure you've downloaded the latest image to get a 1.01 or newer version of the compiler. Now, Plasma does all of its internal calculations in 16-bit words. Characters are promoted to words when processed. When a value is stored to a byte or character, only the least significant byte is saved in memory. If it were greater than 255 or less than 0, the value in memory may not be what you expect. Because Plasma treats bytes characters as unsigned 8-bit values, there may be a situation when you want to work with a value as a signed 8-bit value. The Plasma runtime library has a routine to sign extend the 8-bit quantity so it can be used as values between negative 128 and 127. So here we go, we've sign extended the value 255, which has its most significant bit set and is sign extended to negative 1. Also, we may want to compare words as unsigned 16-bit quantities. There are 4 library routines to do unsigned comparisons. Here's one of them, the is unsigned greater than. Now, negative 1 here actually will be treated as an unsigned 65,535. When we compile this and run it, we will print out the value of true or false. Under Plasma, false is 0 and true is negative 1. And here we saw negative 1 being printed out, meaning true, so indeed it did the unsigned comparison. And lastly, here we have Plasma using hexadecimal constants. If you're an assembly language programmer, you will be familiar with this notation. Using the $sign in front of a number treats it as a hexadecimal number. Here's the speaker address for the I/O location to click the speaker on the Apple II. You may see that in some of the source code that makes noise. But we can treat them as just any type of constant, and to show that we get the right value, let's just print as an integer a hexadecimal number. It's not money, it's the $sign is for hexadecimal. So hexadecimal 100, if you're good at your conversion in your head, is, as soon as I type it out right, and wait for it to compile. And it is 256. Okay, so byte, chars, and word var are the only data types Plasma natively works with. We will see in the next episode how this translates in the ability to manipulate data structures and pointers. So thanks for watching. Hope you enjoyed it.